Hi, my name is Tom Hall, and I'm an associate professor of mathematics at Western New England University. And I am in this video making videos of my research. My research is on origami mathematics, and I want this one to be about a paper that came out in 2020 about rigid origami, rigid foldability of origami, and showing that it is hard in the theoretical computer science sense. So let me try to explain what the paper is about and what the research is about. Okay, so first, what is rigid origami? Rigid origami is where we have some kind of crease pattern and we want to fold it as if the paper was actually made out of sheet metal and the creases were just hinges, you know? And so a very simple thing like would be just folding a piece of paper like this. That would be easy to do with sheet metal. You just make two rectangles, two 1x2 rectangles. Put hinges between them and you'd be able to fold that, right? But not all crease patterns are rigidly foldable. Not everything you can do with origami, like for example, this paper crane could be made if I did it out of sheet metal and put hinges for the creases. Even something as simple like this is a little difficult. Like, look at this. This is just 4 creases with 9-degree angles between them. And you can prove that there's no way for me to fold this rigidly using all 4 creases at the same time. I mean, I can do this. I could fold in half and then in half again. That would work as long as you accommodated for the thickness, but we're going to ignore the thickness of the paper, okay? This is mathematically thin paper for the purposes of our proofs and stuff. So I could do that. I could do it sequentially, one and then another, but I couldn't do all 4 at the same time. That forces the paper to bend and stuff, and that's not good. That's not rigid. That's not rigidly foldable. Another example, a more complicated example that's relevant to our paper is this. This is called a square twist. This is a really cool origami crease pattern. I'm going to unfold it to show you what it looks like. Ooh, yeah. So it's got a square in the middle, and then these pleats coming out north, south, east, and west. These 2 parallel pleats here. See. And it's very symmetric like that, but there's this square or diamond in the middle, okay? And notice that I'm making it all mountain creases around that inner square. If I do that, this does not fold rigidly. Look, it really wants the paper, it actually wants it to bend right along that middle, which I'm assuming that's not part of my crease pattern. I only want to fold these lines that I drew on here, okay? Nothing else. And so if I try to fold this without doing that, like keeping that middle face rigid, then look at what's happening to the rest of it. It's all curling around and stuff. So this crease pattern with this mountain valley assignment is not rigidly foldable. But if I change up the mountains and valleys, if I say push this one in and that one out, let's see if I can do this. And I can get it to rigidly fold. I mean, it's a little hard to see because this paper is kind of floppy, but I can get it to, like, now it doesn't look nearly as bad as it opens and closes. You could maybe imagine, I mean, this one may be torquing a bit in my hand, but you could imagine maybe this actually would work if made out of sheet metal. But notice it's a different collection of mountains and valleys. Here I have now 3 mountains and 1 valley in the middle there. Okay, so you can prove that this one actually you could make out of sheet metal. All right, so the question we address in this paper is, how hard is it to tell from a crease pattern whether you could actually rigidly fold it? Like how difficult is that? And this was of concern because engineers have been very interested in these types of origami mechanisms you can make. Like the idea is that things like this you could use to do robotics or other kind of machinery applications. And origami is a lot of appealing things to it. If you could get this to work out of sheet metal, it'd be very easy to fabricate. It's flat. You just have to, like, you know, do things on a flat surface and then if you could get it to fold up in some complicated way, that would, imagine you could build a robot or some kind of piece of machinery that starts flat, easy to manufacture, and then just whoop, turns into the machine you want, or that gives you the motion that you want. So that, you know, people are interested in this for deploying things in outer space, building little robots, all sorts of things, okay? So, but when engineers actually do this, they run into problems. Some of them have to do it like, oh, we wanted this thing to fold, but it's not rigidly foldable, so that doesn't work. So there are these hurdles to overcome, and that's where the math comes in. Okay, so what we did in our paper, and I'm going to share my screen. What we did in our paper is we tried to address this question. We tried to address this question of how hard would it be to tell if I actually folded, had a crease pattern and wanted to see if I could rigidly fold it. So the title of our paper is Rigid Foldability is NP Hard. And so this is where you need to know a little bit of theoretical computer science, how in computer science they classify problems as difficult or not by comparing them to other problems that are at least as difficult or people believe are at least as difficult. Hard problems like the traveling salesperson problem or getting a computer to play perfect chess or something like those are considered hard problems. It's hard to get a computer to do them quickly. They take more and more time for the program to run if you put a lot of inputs in. So by saying rigid foldability is NP hard, we're saying that this question, give me a crease pattern, can you tell if it rigidly fold, is at least as hard as other hard problems. We're saying it's hard. That's it isn't something that is really easy to do for a computer, say, or for us to determine as humans. So this is a paper, this is work put together by a lot of different people. Hugo Akitaya, Eric Demain, Takashi Horiyama, me, Jason Ku, and Tomohiro Tachi. We all worked on this at some research workshops, and but the paper only came out last year because it took a while to hammer out the details. So this was published in the Journal of Computational Geometry, and I'll show you the link to it later if you want to see. But let me kind of explain how this goes. The way in which you show that something is difficult is like I said, you show it's equivalent to a known hard problem. And what we do is show that it's we reduce this problem, and actually we take a slightly different tack on it. We say, like, okay, suppose you have a whole bunch of creases, and kind of like with this this simple crease pattern where we could rigidly fold it if we only use some of the creases but not all of them. We ask the question, if the crease lines are optional, if some creases are optional, I don't have to fold them all, but can I fold some of them into something rigid? Even doing that is hard. Okay, strongly NP hard. We do that by showing that it's equivalent, that if I could do this rigid origami problem, then that would be equivalent to solving a classic problem called positive 1 in exactly 3 satisfiability. That's this thing here, positive 1 in E3 sat. Okay, what's that? Well, this is technical stuff. I'll gloss over it, but the idea is it's a logic problem. You imagine you have all these logic variables, that is, variables that are either true or false, or 1 and 0, like logic, true or false, okay? And we have all these variables, and they're called like x1, x2, x3, or something like that. Each one could be true or false, okay? And then we have a whole bunch of clauses. These clauses have combinations of 3 variables in them, okay? So I might take variable x1, x4, and x9, and I make a clause out of it, okay? And I do that for a whole bunch of triples, okay? That's the 1 and 3 part, okay? We're taking triples of variables, and the question is, can you find true and false values for all your variables that will make all your clauses true? And here, true means I want exactly one of the variables to be true. That's 1 in exactly 3 satisfiability. I want only one of them to be true. So I have all these clauses, I have all these variables, and the clauses will overlap with the variables, and there could be lots and lots and lots of them. Okay, that's actually, so finding true and false values for the variables that make all the clauses be 1 in exactly 3 true is a known hard problem. And what we did is by playing with origami a lot and playing with some of these square twists, although it's slightly different, notice these aren't exactly the same square twists, we came up with a huge crease pattern. I'm going to show you a picture of it. There's a lot of technical details in this paper, but yeah, here's a huge schematic of a crease pattern where we have, I'm going to zoom in on part of it, where we have some input variables, and I'll explain those in a second. And notice that there are all these overlapping lines, but that's because we're allowing optional creases, okay? But the idea is that this whole crease pattern will only fold rigidly if and only if I have a valid solution to this 1 in exactly 3 sat problem. Okay, that is how we're trying to reduce, we're trying to say, oh, here's a crease pattern, And if I could rigidly fold it with optional creases, then I could solve an equivalent arbitrary 1 in 3 sat problem. So you give me a 1 in 3 sat, 1 in exactly 3 sat problem. I could turn it into a crease pattern, and if I could rigidly fold that, I'd solve your problem. That's how we show their equivalent. That's how we reduce rigid foldability to this known hard thing. That's how it works. So let me quickly show you how we do this. You know, how do we translate the logic into origami? That's kind of like the cool part. That's like the paper folding part. Okay, so the idea is how do we take these true and false variables? We do this by creating these things called wires, and wires look literally like this. They're 2 parallel pleats, and these could be really thin, really skinny. Okay, but two parallel pleats, and I will either fold them or not. If I fold them, that's true. If I don't fold them, that's false. That is how it works. Okay, and folding them could happen in several different ways. We'll see how this works later, but this would be one way to fold them. Okay, these pleats are so close together that they have to be mountain valley. Okay, if I had 2 mountains, then the paper might collide into itself really fast. So we're keeping them like this would be one way to fold it, like valley, mountain, and then mountain, valley, to make it like a trench or a trough or something like that. But it could fold all the way if I wanted it to. Okay, but I don't have to fold the pleats this way for it to be true. This is one way to fold it true. Another way would be like this. This is called a staircase wire, and they're still folding, but notice one of them is folding a lot faster than the other. I'll get at that in a second as to why we care about that. But this is still the same parallel pleats, just folded a different way. Now it's mountain, valley, instead of valley, mountain, valley. You know, that's just a different pattern. But both of these would be considered true. Okay, so those are my wires. Those are, in fact, here at this part where it says variables, let me zoom in on that. Those are my input variables. And here I have 4 of them, x1, x2, x3, x4. Notice that we have these pairs of parallel lines. So if I want x4 to be true, that means I have to fold those 4 creases right there. If I want x3 to be true, I want to fold those 4 creases. If x2 is false, I don't fold those. I just don't fold them. Okay, that is how we would go back and forth between the logic and the crease pattern there. Okay, but look at all these other things. Look, there's square twists and stuff. So what's that all about? Well, when we make these parallel pleats, we also going to want to have some pleats going up and down as opposed to left and right. So, and we want these square twists, well, they will trigger that. So if x2 is true, then I'll have some lines going across, folding horizontally, and that will trigger, say that it could trigger this one to also fold, which would send some pleats going up. Okay, now how would that work? So these are called crossover gadgets. These are where we and they're built on these square twists, which notice are not exactly like the square twist I showed you. The one I showed you had the vertical lines going like they were like totally lined up with each other. This here, the inner square, like let me actually show you. Here, my inner square is like perfectly straight up and down. This one has been twisted a little bit, and that's done for a reason. Here, if I fold this is folding in one of the rigidly folded ways that the square twist can fold. And here I'm demonstrating that, look, this really can fold rigidly. But what's being done is that, see if I get this right, that the vertical pleats are folding faster than the horizontal pleats. This square twist is making that happen, and that's really important. Okay, so let me see if I can demonstrate that. If I were to fold, in fact, I think they're going twice as fast. So if I look at these horizontal pleats, like look at them head on, and suppose I fold it at, so here it's not folded at all. And then if I fold it so that the crease at the edge there is at like a 45-degree angle about, say that looks like maybe a 45-degree angle from where it was flat, then this is close to a 90-degree angle. Yeah, that's close to a 90. It's not exact. I couldn't get it exact. But there, that's 90 degrees. And now this one here is something like 45 degrees. That's telling you that the horizontal pleats here are going, or the vertical pleats are going twice as fast as the horizontal pleats. So that's controlling the speed at which the creases are folding. That's really important for rigid foldability. Okay, so this is one of the ways in which we have the square twist fold. But another way is this way, which is really the same, but now there's more complicated things going on. We have, I think, some of these are folding really fast, and others slower still. Like, look, this one here folded, it's almost at 90 Here, let me fold it so that it gets to 90 degrees. Yeah, that one down here. And the one at the top is at 90 degrees, I think. This is looking like 45 degrees. Or maybe this one's looking at 45 degrees. But yeah, or maybe they're slower. Yeah, hard to say. But this is a slightly different way of folding it. In fact, you can tell because the one above going around has valley, valley, mountain, mountain, two mountains, two valleys. And this one has, let's look at it. 1, 2, 3 valleys and 1 mountain. 3 valleys and 1. So they are different. And they got some different folding speeds going on between these two cases. Okay, but anyway, we put them together to make these crossover gadgets. That's what I was showing you in this crease pattern. When we have these horizontal pleats and these vertical pleats intersecting, they still got to be able to fold rigidly. And this is how we do it. And we can actually control the way that it happens, which is nice. So notice here we have a pair of parallel pleats going vertically and then another pair of parallel pleats going horizontally. These square twists let them kind of fold together. And here, this is having them both be these trenches, okay? The trench way of folding the wires. Whereas this one has a combination of a trench going horizontally and a staircase going vertically. So we can combine those two. And notice the staircase. The staircase has a lot of different folding speeds going on. Here, these are like 90-degree angles. This maybe looks like it's close to 45. But then this one here is much more shallow than that. So we have lots of different folding speeds going on. That is kind of necessary in order to control the staircase versus the trough. So that's why we have to keep track of these different folding speeds. And then we have this thing, which is part of a folding gadget. So let me explain that. Okay, so now we're ready to kind of talk about how the crease pattern works, all right? So the idea is that if one of these variables are true, okay, then the way this is going to work is it's going to trigger one of these crossover gadgets, because I don't know if you can tell, but the horizontal creases do not go all the way through, okay? They go through some of these, so this crossover gadget could fold if it needed to, but it doesn't have to because these horizontal pleats go all the way through, okay? But then they stop here. So if this X2 is folded, then that will trigger this one to fold and send a line vertically up. Okay, it'll get triggered. But also, this one will get triggered too because the crease does not go all the way through here. It'll force this square twist to crease. So if X2 is true and these parallel pleats fold, then it will send a set of parallel pleats folding up, okay? And it will also trigger this one to fold up. That's if X2 is true. Similar things will happen to X1 and X4 for this block here. There are other blocks that will control X1, X3, and X4, and we can do any combination like that we want. Okay, now why do we do that? Because we want to send those pleats, like for example here. So this is actually controlling a clause. This is taking 3 of the variables, X1, X2, and X4, and if one of them is true, it's going to send that up, okay? And then in this gadget here, if one of these are true, okay, then it will also send it horizontally to this thing, which is called a clause gadget. This long vertical thing, that's called a clause gadget, okay? Now look at that thing, that's weird. What's going on here? It's got a lot of vertical pleats that are really close together, but remember, if one of the variables is true, if any of the variables is true, then these pleats coming up from the bottom will be activated. They will be folded, and that'll activate this clause. And so what's going to happen with this clause? There's another picture that kind of explains how the clause gadget works. So let me find that. Yeah, well, this is the part that's at the top. We'll get back to that in a second. But the clause gadgets, where are they? They're here. Yes, the clause gadgets. Yeah. Okay, so the way the clause gadgets work is that if one of them is folded, okay, then what can happen? Well, we're going to always have pleats at the bottom that have been activated, okay? And the pleats at the top, the way this is designed, the top part will also always get activated. And that's important because that's going to send the pleats up to the next clause, because we're going to have a stack of different clauses, okay? Now remember, this is supposed to be 1 and exactly 3 satisfiability. So we want 1 of these chunks in the middle here, that either the bottom, the second one here, or the third one there, we want one and only one of those to actually activate, and that will represent the clause. Okay, so if this clause was, say, if this bottom represented variable x1, if this one represented, I don't know, variable x2, and this was x4, then I would want exactly one of these to fold. And the way this clause gadget works is that this will fold rigidly if and only if exactly one of these three sections is being folded, either the bottom one, in which case this is the crease pattern. So notice if the bottom one gets activated, then it sends these vertical lines that block the other two from folding. That's what these vertical lines that are closest to the boundary are doing. Okay, but if that bottom one doesn't fold, then the pleats coming up from the bottom will go completely over that bottom section and go to this section, and that section could fold. That would be the second, that would be the variable x2 folding. Okay, and then it sends up these pleats that then block the next one from folding. Okay, but if neither of those two fold, then I want the top one to fold, and there it has to, because these pleats end there, they don't carry on through. So that would then force this one to fold and hook up with this, which will always fold, and then reset the wires to the proper thickness or separation for the next gadget. So keeping that in mind, that exactly one of these three pieces has to fold. Let's go back to the big crease pattern now to see how that fits in with everything. Yeah, because here, zooming in again, like so here we were paying attention to variables x1, x2, and x4. If one of them is folded, okay, then it will send pleats up here, and they will in turn send their pleats horizontally to this clause gadget. But this clause gadget can only fold if one of them are true. That's what we just saw in the clause gadget. It only allows one of these blocks to be true. So this clause gadget will only fold if and only if exactly one of x1, x2, and x4 were activated. In other words, if only one of them was declared true by our input wires. That will make this clause gadget hold, okay? So that's just one clause gadget. If I had another one, like here, this is x1, x3, x4, it sends their wires up to the next clause gadget, okay? So this clause gadget up here would have, you know, these x1, x2, and x3 coming in. It will only fold if it will fold if and only if exactly one of those is true. Okay, and this is a relatively simple case. We only have 4 input variables, but you could imagine having lots more, bigger stack of input variables and a bigger stack of clause gadgets. It's just going to be a huge crease pattern. And it almost it's a type of origami called an origami tessellation. So it's actually kind of cool. Okay, so, but the way these things fold, that's how they work. And in fact, here's a little animation I made of all of these different gadgets folding together, which is kind of cute. Okay, so I hope that made sense. If you want more details, well, you can look at this paper, and I will include the link with this video. So or you can just Google Journal of Computational Geometry. This appeared in 2020, so you could look in that year. But I will include the link. And but another thing, this is a very technical paper, and it goes over a lot more details about exactly what we proved as far as what's weakly NP hard, what's strongly NP hard, what happens if you have optional creases versus folding all the creases. There's still some things we don't know about this, but we tried to cover a lot of the bases. Okay, so the paper itself is the most complete and technical version you could read of this. If you want a different summary in writing, you could look at my book, Origametry. I do summarize that proof in this book, but for the full details, see the paper. And I have to say that one organization I have to thank for this is the National Science Foundation. They helped fund my contributions to this research. So thanks for listening. Thanks for taking the time to hear about origami and mathematics. And we'll see if I make any other videos about my research as we go along. I'll try, but we'll see. Okay, bye-bye.